So I'm going to talk a little bit about that very first module that I built for the active inference brain and how it became sort of an inspiration for creating an entire loop that can power a robot or some other type of artificial creature. I was very inspired back in 2012 when I saw this paper and an accompanying website and videos come out called Playful Machines. This to me just blew up my mind with imagination and the idea that you could build these very simple machines that could interact with their environment and behaviors emerge from that, right? And one of the key takeaway terms is the idea of homeokinesis. Well, you've heard of homeostasis. Homeostasis means that all of your states in your system, like all of the hormones and the various chemicals inside of your body, your body's trying to maintain homeostasis to keep everything in balance so that it stays stable, right? Well, homeokinesis is different than that in that all of your different systems need to be on the edge of chaos, right? You need to be right on the edge of almost falling apart and having noise, and right on the edge of being able to take action and do something interesting, right? Because if you try to optimize a system for homeostasis, well, you end up with a rock, right? It's not very exciting. The most stable system is one that just sits there and does nothing. And that's called the lazy robot syndrome. So we always have to be fighting lazy robot system. And you do that with the idea of homeokinesis, always being on the edge of chaos and movement, right? The other one is the idea of time loop error. And that's the idea of predicting the future just a little bit in order to update your system and stay on the edge of chaos. And I'll explain more about that later. The other huge thing that really unlocked this whole idea in my brain is called JEPA. Now, JEPA is an idea that's been around for a long time as well. It's been championed by Yann LeCun, who is the Turing Award winner, amazing AI scientist who has his own lab now called Amy. And it is the idea called joint embedding predictive architecture that really add up to two main ideas. Playful Machines brings the idea of surprise into a brain. JEPA brings the idea of predicting the future and having a memory that has nothing to do with language, right? As humans, we really have a tendency to think that language is what defines our intelligence. It is absolutely not the case, right? There are plenty of animals in this world that are extremely physically intelligent, but have no way of talking, right? So intelligence lives well below language. Language is what we do as another layer on top of it in order to tell stories, communicate with others, and predict much, much farther into the future. We're not trying to do that. We're trying to actually stay pretty local right now. We're trying to stay very short in time, kind of like a goldfish. And I always come back to those bumblebees that are buzzing around in my backyard that can really do amazing things. So now we can get into one of the coolest aspects of this project, which is the very first module that I built, which is called EPM, which is the Episodic Predictive Memory module. And the way it works is by combining Playful Machines and JEPA. So let's imagine that we've got sensory input coming in from, we'll just say it's vision for now, right? So we've got all these pixels coming in from the outside world. We'll call it every 60 milliseconds. That's our tick rate, right? So that's basically the same as a video. That's our video feed coming in from a camera. And the first thing that those pixels are going to hit is an encoder, right? So remember, the idea with JEPA and our whole active inference concept is that we don't want to be dealing with all of the information in our environment. That's way too much. We need to not just compress the information, it needs to mean something to us at every single moment in time. Now, we do that using an encoder. So I've experimented with all different types of encoders. There's pre-trained encoders, which I believe JEPA usually demonstrates, right? So if you see that person who's making the salad, each one of those nodes or the areas in the nodes correspond to different things that have already happened. They've been trained or they've been labeled by humans. Now, we want to avoid language completely, right? This is a subconscious brain that we're trying to build. So what we're going to be doing is using a frozen encoder, or really a geometric, or basically a generic encoder that you can put pixels into, you can put sound into, you can put, instrumentation into, such as gyroscopes and compasses and accelerometers, and it's just going to turn it into an embedding. An embedding is a list of numbers, right? So a list of numbers, right now our brain uses 128 dimensions, right? That just means that each number has a value between 0 and 1, or -1 and 1, something like that, where it's just a list, and that's an embedding. It represents that state at that time, but it's detailed enough so that you can do something with it, right? So what do you do after you've encoded into that 128 dimension embedding? Well, the next thing is to predict, have I seen that embedding before, or is this something new? And that is by using a forward and backward predictor. So we're just going to give that, forwards, F, backwards, and it's going to be predicting, right? That is going to tell us, am I surprised? And keep in mind, this forward and backward predictor is very short. It has a very short memory. It's just like a little multi-layer perceptron or some other type of a learnable component that can update its weights extremely fast, right? It's very, very small. It just needs to know, like within the past few seconds, have I seen this embedding before or not, right? And what it's going to generate is this idea of TLE, right? That's our time loop error. So that time loop error is extremely important for all of the next steps moving forward. So now that we have our time loop error that's popped out of our forward and backward predictor, we're going to put that embedding into a knowledge graph, right? So a knowledge graph holds all of these different embeddings, or puts a node into the graph that's similar to these embeddings, right? So the idea of having a knowledge graph is that you start to build up these areas of interest, right? So for example, if I'm facing a blue wall and the area of my maze has lots of blue in it, it may group together in this idea called blue. And if I'm near green food, every time I'm near or I'm looking at green food, it may start to coalesce over here, right? These are some examples of when it's vision, but keep in mind, we're putting our embedding into this growing neural gas. So this is called a GNG. I experimented with several different types of networks like this. Well, Claude and I experimented with them. And the GNG seems to be one that just works, right? Just like our frozen encoder up here, right? Our encoder is generic. The knowledge graph is generic. Everything needs to be generic because we want our EPM module to be a generic component in a brain, right? So this is the E. So that is the E of our EPM, and this is the P, and this is the M. This is the memory part, right? E, P, M, right? So the embedding or the episode comes in, we say, am I surprised? And then we put it into the graph. Now, if I'm surprised, it's going to go into the graph, with the TLE value that it knows about, right? So if I'm surprised, it's going to get shoved into that graph. If I'm not surprised, it's more likely to not actually go in the graph, right? But every single time that embedding gets compared to other nodes that are already in the graph. And that's how we build up a memory. Every time a node's been revisited, right? And this is something that we can adjust kind of, it can be automatically adjusted, which is always better for this kind of brain, or it can be something that we tune. We want to stay away from tuning, and you'll see later on in the series why. But the idea is that when an embedding comes in, we want to find out what its neighbors are, right? And we do that using a concept called principal component analysis, called PCA. And that part's very important. That determines the distance. I'm just going to stick that little guy over here. It went through principal component analysis in order to tell where in this graph that embedding actually lives. And that's how I determine whether or not it's close to another node, right? So if I'm surprised in the moment, it'll go through PCA, it gets put into the graph in a certain location, right, in 2 dimensions, and it just so happens to be right next to another node that I've seen over and over and over and over again, right? Yeah, maybe I wasn't expecting to see a hamburger to my left at that time. I was like, oh, look, a hamburger. I know what a hamburger is, though, right? So it's not new across a long distance. It was just new in that short time, right? So, it's like this, the growing neural gas, the knowledge graph is sort of a long-term memory. The TLE is a very short-term memory. And we use that constantly every single tick, right? We have our refresh rate. So once we have, at the end of the tick, I'm going to emit a thing called a reality token, right? RT. Now, the reality token contains all of the information that has happened so far, right? So we take our TLE. Oops. So the TLE comes out. That goes into the reality token. Now, if you think about it, what is TLE? It's sort of like dopamine, right? It's a state of arousal for the moment that I'm in right now. Oh, I was surprised a little bit, right? I want to know that. I want my whole brain to know that my eyes were surprised by the thing that I just saw, right? And we also want to know if other parts of our sensory arrays are surprised or not, right? So that momentary surprise gets baked into the reality token before it gets emitted. The other thing that goes into the reality token is the embedding and the identifier of the node that it was closest to at the time, right? So if I was visiting node number 1224, that gets put into the reality token for that tick. Now, we also know other things about that reality token. How old is that reality token, right? If it's something that I've seen millions of times, well, we're going to know that, right? It's got a very long history. It's been baked for a long time, and it's been visited for a long time. Now, another thing that's valuable is, well, what were the past nodes that I visited in the neural graph at the time, right? So maybe it went here, and then finally arrived at this node. That's the history of the traversal of the knowledge graph, and that goes into the reality token as well, right? So all of these things combine. So we start up here at the top, and we've got our sensory input. It gets encoded into the thing called the embedding. We calculate our time loop error, our surprise. If it's surprising, that embedding goes into the neural graph. Also, keep in mind, the neural graph also communicates back to this TLE. So the TLE can actually be modified. It's like, hey, I was surprised. Well, no, you really weren't surprised. you just landed in a place that I've seen many, many times, and that can actually modify the TLE down. So the TLE that actually shows up in the reality token here may be much more muted than it was right at that specific instance, right? So the TLE is an active loop in and of itself, right? But really the big takeaway here is that we've got our senses come in, they go into the world model for that particular sense, and then they're output as a reality token. Now, what do you do with all of these reality tokens? That's going to be part of another video, but think about what's possible now when you have this idea of an EPM, right? That module is able to do a whole lot of heavy lifting when it comes to taking all of that information in the universe and bringing it down into a common language that other modules in the brain can understand. Now, the brain that I built is just a C++ publish and subscribe design pattern, right? We have all these different modules. They can publish their reality tokens onto a bus that all of the other modules can read from, right? And they can publish onto the bus too. And they have whitelisting, and they really only read the things that they need to read. So that covers, I think that's plenty for now to talk about what is the EPM module and why it's important. And the next couple videos are going to be about how my first pass at building the EPM, what I tried to do with it, and how this whole idea started to morph from, okay, I've got this EPM module, now what do I do with it? How can I make this thing do things in the active inference context? So check it out.